So in the previous session, we saw that most problems are undecidable for parametric time automata, but there are some decidable subclasses. In this session, we will talk about parameter synthesis algorithms. Let us go back to time automata without parameters. Since we have dense time, since we have real-valued clocks, we have an infinite number of possible behaviors because we can choose any real value for the time elapsing, and so we have an infinite number of symbolic states, of concrete states. And so the objective will be to group all concrete states reachable by the same sequence of discrete actions together. So we will have symbolic states, and a symbolic state is a discrete part, so this is a current location, and an infinite set of states grouped into a symbolic manner. And for time automata, Z can be represented by a convex polyhedron, which we call a zone, with constraint of the form, a constant smaller than a clock, smaller than another constant, and a different of clocks, so xy minus xj, smaller than a constant. We can do a symbolic computation of those successively reachable states using operations on polyhedra. So for instance, for one edge, going from location L to L prime with action A, guarded by G and resetting the set of clocks R, we have that the successor of this zone, so discrete part, continuous part via this edge, will be L prime, of course, as a target location. And what happens for this symbolic part? We first take the intersection of the zone with the guard. We reset all the clocks in R to 0, so we replace the value with 0. Then we intersect with the target invariant. We apply some operation called time elapsing. Time elapsing means all the clock can move together at the same rate. And then again we intersect with the target invariant. And so with some additional technicity, which is linked to the K abstraction, we will have a finite number of reachable zones in a time automaton. So a small example for symbolic states in a time automaton. So I have a small time automaton when y is smaller than 4, so this would be my initial symbolic state. Both clocks have the same value because they are initially 0 and they're bounded by 4. Okay? And I will take a transition when the guard is such that x should be greater or equal to 2, and I will reset y. So I start from this. I intersect with the guard, so only this part is kept. Then I apply the reset, so I reset y, meaning that both, so the 2 dimension becomes a 1-dimensional constraint because y is 0. Then I apply time elapsing, so I can be anywhere there. And finally, I intersect with the target invariant, but I have no target invariant, so I stop here. For parametric time automata, we can do the same, almost. A symbolic state will be a discrete part, so a location, and a continuous part, which is again a convex polyhedron, this time containing not only clocks, but also some parameters. It's a straightforward extension of reset and future that act only on the clock variables. The convex polyhedra have a special form that are called a parametric zone, and they were studied 15 years ago. So if I take this example, which looks a bit like the previous one, the initial parametric zone will be both clocks are equal. Of course, y is smaller than p, and both parameters are non-negative because I chose my parameters to be non-negative. In the target zone, we can do some computation and we get something like this. So x minus y is compressed into 2 parameters. We know that q must be smaller than p, and then again, all variables are greater or equal to 0. A main difference, though, is that we have in general an infinite number of symbolic states in a parametric time automaton, and this is in contrast with time automata, where we have a finite number of symbolic states. Thanks to this symbolic construction, we can design a semi-algorithm for parametric reachability in parametric time automata. So we'll call it EF because this is reachability. G here is the target location. So I'm looking for all the parameter evaluations for which I can reach a symbolic state in which the discrete part is in this set of locations. My algorithm takes 2 sets. So S is the current state, and M is the list of visited states so far. It's just to avoid to visit 2 times the same one. First, S, so S is actually LC, okay? And if L, my current location, belongs to the goal locations, then I finished, and I return the projection of the zone, so LZ, so L is the zone, projected so on to the parameters. If S belongs to M is a set of visited states, then I visited already S. I don't do anything, I return nothing. Otherwise, I will compute the successor and iteratively apply EF to the successor states. So I will take the union for all the edge over the successor of S via this edge of the recursive call to EF with the new state S prime, and of course I don't forget to add S to the list of visited states. So EF collects the parametric reachability condition of all the symbolic states with a goal location. If the algorithm terminates, this algorithm is correct. There is no bad valuation that is returned, meaning all the valuations synthesized are such that the goal locations are reachable, and it is complete. All the valuations for which we can reach the goal are inside the return constraint. However, of course, termination is not guaranteed because the decision problem, you remember, the EF emptiness problem is undecidable. If we were able to synthesize all the valuations, then we could solve EF emptiness, and that would go against the fact that it is undecidable. So EF synthesis, so this algorithm, is the most basic synthesis semi-algorithm for parametric time automata. However, we can still ensure termination using some approximation, using the notion of the integer hull. So what is the integer hull? Integer hull is if you have a polyhedron, whatever dimensions, you would take all the integer points in your polyhedron and take the smallest convex constraint that contains all those points. So like this here. Okay? And if you apply at selected places the integer hull operation, you ensure termination of EF. However, there is a drawback at the cost of completeness. There is no free lunch. We cannot get both completeness and correctness. So we keep the correctness, but we lose the completeness, and we gain termination. It only works for bounded parameters, even if it's dense, even if it's rational valued, we have bounds on the parameters, and we are sure to preserve all the integer points in this bounded domain. So we return all the integer points, and sometimes, often actually, more than the integer point, we get most of the rational points as well. We also designed similar semi-algorithms for more complex properties, such that the inevitability and also the language preservation. So this EFSynth algorithm is implemented in 2 state-of-the-art tools, so Imitator for parametric time automata and Romeo for parametric time Petri nets, which is a formalism very similar to parametric time automata. Let us now study a second algorithm. The trace preservation synthesis is the one that preserves the untimed behavior. So the trace preservation problem, we saw it a bit earlier, called language preservation, which is very close. So given a parametric time automaton and a parameter valuation V, we will synthesize all the valuations with the same time abstract behavior. So by here, trace set we means an alternating sequence of locations and actions. So here in 2 dimensions, we have a valuation V0, and we will exhibit other valuations around in a symbolic manner with the same time abstract behavior. This is linked to robustness, meaning that if V0 moves a bit in this pink part, we will still have the same time abstract behavior, same set of trace. How does the trace preservation synthesis work? There are 2 parts. We'll first forbit the incompatible behaviors, those that are not in the reference valuation, and then we will require that all those behaviors actually happen. So basically there are no deadlocks. We start with a true constraint, and then we will iteratively compute sets of reachable symbolic states, and we will refine the constraint by removing incompatible state from S. So incompatible state is one for which the symbolic part does not contain V0. and we add the negation, and we do it again until there are no more incompatible states. And then the second part is very simple. We take the intersection of all the symbolic constraints, the parametric symbolic constraints for all the reachable states, and then we are sure that all the states will be reachable. So, as an example, let me consider an asynchronous circuit. We can model asynchronous circuits using parametric time automata. So we have 4 elements, sometimes made of several gates. So this one is one element, this is the second one, third one here, and last one there. So we have 4 elements. We have 2 input signals, G here and CK. You notice there's loops, meaning that the output of G1 is an input of G2, and the output of G2 is an input of G1. We have an output signal here, Q. We have timing delays, so the traversal of each gate is not instantaneous. If there is a change in the input, the output will change after exactly 7 time units, or here between 3 and 7, and so on. We have environmental timing constants. We know that, for instance, CK, the clock, will remain 15 time units in the lower state and 24 in the higher state. And we know that D is stable at least 10 and at least 17 after the rise of the clocks. So, as a question, for these timing delays, does the rise of the output signal Q always occur before the fall of CK? So does it occur in here and not after there? We can use time model checking. We have time automata, we have no parameters yet. So we can use a time model checker, model the system, check, and then get the answer. The answer is yes. This system is correct for those valuations. Now I will replace my timing constant with parameters. So now I don't know those values. They get parameters both for the environment and for the traversal delays. And the question is, which values of the parameters yield the same untimed behavior as the reference valuation? And the untimed behavior also means that if the rise of Q always occur before the fall of CK, it will be the same for the other valuations. So a trace set is a set of all traces. We represent it in the form of a tree. It doesn't give information on branching behavior, but it's so here we have 2 traces. And so we will apply a symbolic analysis starting from the initial state. I already eliminated the clock values here. I just keep the parameter valuation. So I already projected onto the parameters. So I start with the initial state, I take this D action, I study, and then I notice that this one is an incompatible state. Why? Because T setup smaller than delta 1 plus is not compatible with the initial valuation. We don't have that 10 is smaller or equal to 7. It means this state is not reachable for the initial valuation, so we have to remove it. So we take the negation of the state and we add it to the constraint. We remove it and we go further, again, an incompatible state, and at the end we also add, this is the second part, we also add the intersection of all the constraints that we met, and we get this big constraint. And for this big constraint, we know that the system is exactly made of those 2 traces, and for both of them, we know that the rise of Q occurs before the fall of CK, so the system is correct. So we found a new set of valuations around my initial parameter valuation with the same correct discrete behavior. There are several software supporting parametric time automata. The first one in the 90s was high-tech by Hensinger that actually handled a larger class of automata, namely hybrid automata with parameters. Favor also is a model checker for hybrid systems. Then Romeo, since the late 2000s, is based on parametric time patronate, which again is very similar to parametric time automata. And finally, Imitator is dedicated to parametric time automata. And for those 2 model checkers, Romeo and Imitator, we will talk about them a bit later. So there have been a number of success stories using parametric time automata despite undecidability. So in the literature, there have been plenty of variants of more or less toy train controllers. There have been real protocols studied and verified, such that the road contention protocol, the bounded retransmission protocol. There were some asynchronous circuits, including from the ST microelectronics chipset manufacturer, verified. There have been more protocols, 4-phase handshake protocol, a distributed prospective architecture of the flight control system of the next generation of spacecraft by Astrium. There have been also music scores analyzed, the alternating bit protocols, plenty of schedulability problems, and lately scalability problem by Thales in a aerial video system where there was some uncertainty in the periods. As a conclusion, we study here two algorithms, EFSynth for parametric reachability and the trace preservation synthesis with a measure of robustness. There are more algorithms in the literature, EFSynth, which is the unavoidability synthesis, and it is implemented in Romeo, the behavioral cartography, and also deadlock checking, non-zero checking, and plenty of others. But all these algorithms are very costly. So, in the next session, we will try to improve the performances with distributed computing.